All right, well, good afternoon, everybody. Thank you for joining us for session number 2 with our second keynote speaker, Dr. Bashar Rizk, known formally as Bashar moving forward. For those of you that could not make the call or the presentation yesterday afternoon, let me just give you Bashar's bio here real quick. Bashar has worked as an applied physicist in a university research and development setting for 40 years in various research and development projects. 35 of those years have been at the University of Arizona Luna and Planetary Laboratory, working on spacecraft, remote sensing systems, design and development testing, calibration, planning and operations, data processing and analysis. Bashar also worked in radiometry, thermal modeling, radiative transfer, photogrammetry, and stereophotoclinometry, ground-based astronomy, noise analysis, integrated circuit fabrication, laser and microwave device system development, and elementary particle physics. Bashar was born in Damascus, Syria, but mostly grew up in cloudy Champaign-Urbana, Illinois, and hazy Greensboro, North Carolina, before he crossed the Mississippi River and the Rocky Mountains and discovered Tucson, Arizona, and its clear nighttime skies. Bashar enjoys spending time with his wife and 2 children, writing and biking. Bashar holds a Bachelor of Science degree in physics and chemistry, a Master's of Science degree in physics, and a PhD in planetary science. I'd like to welcome again Bashar to the group, and believe you're going to continue on where you left off yesterday. So
thank you so much for that really generous introduction. Thank you. Let's see if I can show this. Are you guys seeing it?
Yep, we are good to go, and we are live on YouTube.
Okay, great. So I'm not going to go through the usual introduction stuff because Kennedy covered all that. I'm just going to launch right into the presentation. Okay, good. So before we get into it, so I promised you yesterday that I'd be talking more about the results of the mission. First, let me pause here. Am I coming through okay? Too loud, too quiet? Kenny, what do you think?
You're doing good.
Okay, good. Then I'm going to keep going here.
Sounds good.
We're going to start by showing you this image of the Earth-Moon system, a little bit of a family portrait that was captured by one of our cameras, the MapCam, in October of 2017 after we did the Earth Gravity Assist flyby. It's a really iconic image. It's one of my favorite images from the mission. You get to see the amount of lonely space there between the Earth and the Moon, and it's even worse when you, and let me click here. If you, the original image is foreshortened, and I'll show you in a second the conditions by which we took it. But when you actually look at it broadside, then you see the amount of distance here between the Earth and the Moon. That's 400,000 kilometers or 250,000 miles. So I want you to remember that. Let me click this off and click the circumstances by which we took the image. So we were climbing out of the plane of the ecliptic after having dived under the south pole of the Earth to get our boost up out of the ecliptic plane. And 10 days later, we looked backward and snapped this image of the Earth and the Moon. You can see the frame outline of the MapCam there. And on the bottom here, left inset, you can kind of see a top-down view. There's the spacecraft about 5.4 million kilometers away. We were booking away from the Earth-Moon system. And this is us looking back at a range of around 5.1 million kilometers and snapping that image. So let's just keep that in mind, and because I'm going to be using that in a second here. Let me get this out of the way here. In 1970, so I'm going to start with a little bit brief description of the background by which we came to visit an asteroid, a near-Earth asteroid like Bennu. In 1970, we only knew about 4,000 asteroids. In the previous 100 to 150 years, we'd only discovered several thousand of them. And we started to get serious. This was the dawn of the space age. I was 11 that year, keenly interested in this, of course, following all the literature. In the next 20 years, we still hadn't increased the amount of asteroids by more than a few more thousand. But in the 90s, we started getting serious about this. And I'm going to, oops, wrong one. I'm going to display this inset chart which shows from a period of around 95 to right now, in fact, yesterday or the day before yesterday, the pace of near-Earth asteroid discoveries. So the near-Earth asteroids are the ones around the Earth here. So let me click this off again. It's clicking in the wrong place. This is a top-down view of the solar system with the sun at the center, Mercury here, Venus there, the Earth there, and Mars there. There's Jupiter down in the lower left corner. This is from a video, YouTube video by Scott Manley, a Scottish gamer, and I urge you to watch it. I included the link down there. It's the full video is 5 minutes, and it basically gives a history of asteroid discovery, and I love showing it. I'm always jumping at the chance to show this video. So after 50 years in 2021, this is the situation now. This is actually from 2015, but the situation in 2021 looks even more crowded. At 51 years later, we're more than 1 million asteroids throughout the solar system, and more than 25,000 of them are near-Earth asteroids. A lot of the new ones are smaller, they're less than 1 kilometer in diameter. This plot, this depiction, as much as I love it, is a little bit of a misleading thing here. Remember, the Earth-Moon system is 200. So between the Earth and the Moon, we're talking about 400,000 kilometers. If you ask yourself, what is the average separation between these green dots of asteroids in the main belt? They're like 4 or 5 Earth-Moon distances apart. That is a lot of empty space. So even though we spend a lot of time watching science fiction movies that depict people running into asteroids, that is clearly not the reality. The reality is there's a ton of empty space between asteroids. Nonetheless, there are still a lot of minor bodies in the solar system. And if we look more closely here, we see the sun, Mercury, Venus, the Earth, and then there's Mars right there, and there's Jupiter in a different position from the original one 50 years before. These red asteroids are what we call the near-Earth asteroids. Those are the asteroids that approach or cross the orbit of the Earth. They're the ones that tend to be the most concerned about, because they're the ones that could potentially hit the Earth. So if I ask what else the asteroids are good for and what we are, I see there's some chats here. So I'm gonna stop and ask some. Oh, you're just prompting for questions there, Kenny. Okay, good, then I'll keep pushing, but please ask questions at any time. And I'm here trying to shove this little information icon away so it doesn't prevent you from seeing. Right there seems to be fine. The asteroids, so I'm starting the videos on this page here, and on the top left, the asteroids have, in the most recent models of solar system formation, figured strongly in affecting the fate of the solar system, which came as a surprise to people in my community a decade and a half ago, when this model, which is, by the way, called the Nice model, because it was first presented by 3 independent groups, all simultaneously at a conference in Nice, France. The early solar system had some really wild astrodynamics. After a period of time, the small bodies of the solar system, when it was created, they had a lot more than are present today. They changed the orbits of the giant planets to the point where we started out with 5 major planets, and one of them got kicked out, as you just saw there, and now we're only left with 4 not in the original positions. So from the point of view of solar system origins, not only are asteroids records of that time period, but they are also major actors during the events of that early period in the solar system's formation. We've already talked about the impact hazard that they present. We already know of one major impact hazard that wiped out most of the life on Earth that happened some 70 million years ago. It wiped out the dinosaurs, famously. Here, the bottom 2 slides depict what a potential reservoir of resources the asteroids represent if we could just get there easily. In fact, asteroids are the easiest objects to get to in the solar system because they don't have much gravity. And so it was decided that we would try to send a mission to one of the near-Earth asteroids to try to not only visit it, study it, but also get a sample. And I'm showing the sample acquisition process of the mission we selected eventually, which was called OSIRIS-REX. OSIRIS-REX was an acronym that stood for origins. That's to study the origin of the solar system, spectral interpretation, try to compare the spectra and data that we would take at the asteroid with what we acquire from the ground, to try to validate both, figure out if there's any resources that we could use when we're sending out space missions or possibly colonizing space, figure out what the details of the non-gravitational forces are that affect the asteroid's trajectory and potentially cause it to crash into the Earth, and then figure out the history of the asteroid by studying its regolith. So these were all major, any one of these things would have been a major thing to try to do, but we wanted to do as much as possible. That's the tendency these days, because these missions are so expensive that you want to cram as much as possible without burdening the mission so much that it fails. The target we selected was 101955. That was its official designation. That's the 101,955th asteroid to get named, to get designated as an official asteroid. It was discovered in 1999 by the survey Linear, which was an automatic survey conducted out of New Mexico. A lot of the surveys are happening in my town, Tucson, Arizona, or in Hawaii these days. The asteroid was named Bennu after a contest that we held. The name was selected by a 10-year-old boy from North Carolina. It's a medium-sized carbonaceous near-Earth asteroid with a medium fast spin. Its rotation state is around 4 hours. 2 hours would have been the too dangerous to go to critical rotation. Its size is small, but not too small, so it still has some gravity that allows us to orbit around it. It's a relatively simple surface. A lot of these asteroids are binary systems, or they have weird potato or peanut shapes. You can imagine that orbiting around something like that would be more complicated. Orbiting around something that's spherical in shape is a lot easier. The bulk density was very close to the density of water, so we hoped that it would not only have carbon and carbon-based compounds there, but potentially some water-based compounds as well. It was dark, 4.5% reflectivity, or even lower, around 3% when we got there, we found, is a very dark thing. So we would have to design sensitive cameras. It shares the space around the sun with the Earth. You can see its orbit here in blue. Every 6 years, it comes back to the same spot, and so does the Earth. They're in a bit of a resonance with each other, 5 to 6 resonance. So it's almost a quasi-satellite of the Earth. So it's easy to get there, because when you get to this point in its orbit, you just launch directly into its orbit, saving yourself a ton of fuel. Getting a sample from this asteroid was the prime directive of this mission. And since laboratory instrumentation is so sensitive these days that you can study stuff down to the atom level. You can look at pieces of a single atom or several atoms and deduce things about the early solar system, which is quite remarkable. So you don't need a ton of material, just 15 grams, and you can answer some fundamental questions. So this allowed us to garner a low-risk posture from NASA's review panel that approved us in the first place, because we didn't need a ton of sample. We were hoping to collect a lot more, but even stuff that just got coded to the exterior of the sample head would have been sufficient to answer a lot of these questions. And I've listed the questions here. Mostly I've talked to most of them. We wanted to know the history of Bennu. We wanted to know whether there are ices and organics there and how they became part of this. Was Bennu a collision fragment? Did it form in place? How did it become a near-Earth asteroid, presumably formed in the main belt? How was material accumulated on the surface of Bennu? And is there any geology happening on Bennu? All these were questions that we wanted to answer. But before we get to that, I wanted to spend a little time talking about why we chose Bennu. And let me check my time. Okay, good. We're doing all right. It was carbonaceous, as I told you, but there was a much more involved process than that. We knew of more than 500,000 asteroids at the time that we were selecting our target. Of those 500,000, only 7,000 were near-Earth asteroids. Now there's more than 25,000, as I mentioned in a slide before. In terms of those that had good orbits for sample return, in other words, that wouldn't be too expensive to go to, that was less than 200. And then we wanted stuff that wasn't a fast rotator. So that reduced it to around 26. In other words, and of those 26, only 5 were carbon rich. So very quickly, we went from 500,000 to 5 by going through this logical process that really doesn't take that long, although you have to know a lot about and catalog a lot of the asteroids that you could potentially be visiting. So it's funny, at the same time as we're doing our mission, the Japanese launched a mission called Hayabusa 2 to a carbon-rich near-Earth asteroid. Also, it looked a lot like Bennu. I don't know if you guys have seen it in the on the web, but it's twice as big, and its name is Ryugu, which in Japanese means Dragon Palace. And it was our backup target. So we collaborated closely with our Japanese colleagues throughout this mission. Their mission is a little bit in advance of ours, so they're due back pretty soon, and they're going to be able to see how much sample they collected. For all intents and purposes, it looks like it was, all appearances, I should say, it looked like it was very successful. On the left there, I have an image that shows you the relative size of Bennu relative to other objects that you might have seen or seen pictures of. Bennu is a hazardous asteroid, and I wanted to go into that a little bit just so you would have some information about that. It is probably the second highest, most hazardous asteroid, but since the first highest isn't due to be hazardous for another 700 years, in the near future, at least within the future that might be experienced by our grandchildren, great-grandchildren, or great-great-grandchildren, Bennu is the most hazardous asteroid. It's got a minus 1.71, and I know it probably doesn't mean much to you, but there's a technical impact hazard scale called the Palermo scale, and it's pretty close to the top there. The hazard happens as a result of an encounter that Bennu will have with the Earth and the Moon system in the year 2135. If it goes through any one of these keyholes, then that practically guarantees an impact on the return, one of the return trips. And those return trips will happen later in the 22nd century. So this is well into the future with lots of time to do something about it, assuming that it's an actual reality. So between 2135 and 2196, that will be the time that we would be preparing any kind of preventative or prophylactic measure to prevent it from hitting the Earth. And I just list the cumulative probabilities there. They're like 1 in 2,700, which is quite high for this kind of stuff. Where did Bennu come from? Well, I already mentioned it came from the main belt, and this is why we believe that. In general, this is the picture that we have for objects like Bennu in terms of its history. I highlight the main points here. They formed in an accretive process at the beginning of the solar system. They were altered as they got bigger. They had parent bodies that were much bigger than them. So Bennu is less than 500 meters in diameter. It probably came from a parent body that was several hundred kilometers in diameter. That is big enough to heat the rock, melt a lot of it, and show some of the alterations that we witness on the surface of Bennu. At some point, this parent body was disrupted, either through collision or tidal effects or whatnot. And Bennu was, or the material that formed Bennu was cast off. Now, Bennu spins backwards, and that's really important because of an effect called the Yorp effect or the Yarkovsky effect. Y in Yorp means Yarkovsky. So there are two slightly different effects that have the same kind of cause. They're non-gravitational forces, and in this case, the non-gravitational force is a thermal asymmetry. It's the heat coming from one part of the asteroid more strongly than it's coming from another part of the asteroid, and not just heat, but reflected light as well. And when that happens, the asteroid can do one of two things, or both things. It can get a little bit of a boost or a little bit of a slowdown in its orbit around the sun, and it can also spin up or spin down depending on the direction of the effect. All that means is if something is orbiting counter rotation to the rest of the solar system, like Bennu is, in other words, backwards, then this effect will tend to slow Bennu down and send it toward the sun, falling a little bit closer to the sun. And that seems to be what happened to Bennu. It started out of the main belt here, and I show the main belt. And before I get too much ahead of myself, I'm going to check time and I'm going to ask for questions. So I'm doing fine, 20 minutes into the talk. Are there any questions so far?
The only question I have here so far is, when you say Bennu spins backwards, is that to us like counterclockwise, clockwise?
If you're looking at it from the top, it's clockwise. Okay. So stuff in the solar system not only spins counterclockwise as you're looking at it from the top, what you would consider the normal view, but it also rotates around the sun or revolves around the sun counterclockwise. That's considered positive angular momentum in the solar system. So that's just, we say it's positive just because we want it all to be aligned with our sort of naive view of it. Does that answer the question, Kenny?
Yes, it does. Thank you.
Okay, cool. So if something is spinning clockwise like Bennu is, then it's going to lose orbital energy. And if it starts out here, like we believe Bennu did, in this center of this blue mass of asteroids here. So here, let me just tell you what I've got plotted here. On the x-axis here is semi-major axis, or distance from the sun effectively, in AU. 1 AU is the distance from the Earth to the sun. So 3 AU is 3 times the distance of the Earth to the sun, and 2 AU is 2 times the distance of the Earth to the sun. So between 2 and 3 AU are most of the main belt asteroids, that huge giant population that I showed a movie of at one of the earlier slides is depicted here by a bunch of points or straight lines going up. So you can see number of asteroids indicated there per 5 10,000ths of an AU bin width. So that's through the beauty of histograms, we can see where it came from between 2.4 and 2.2 and 2.4 AU, somewhere in this neighborhood here. It's either part of the Eulalia or Nupalana families, we believe. So starting out from these asteroid families, the Yorp effect makes it go this direction, and eventually it hits a resonance with other asteroids, with the sun, with Saturn, with Jupiter. It hits a resonance that causes it to be kicked out of the asteroid belt. Now, most of the time, that's a death sentence for asteroids. Either they'll spiral into the sun or they'll be kicked out into the Oort cloud, into the outer solar system. I guess the latter isn't really much of a death sentence, but it's the difference between a hot death, very quick, or it's a long, slow, cold death, or cold storage. Neither of those things happened to Bennu. Instead, through a later encounter, probably with Mars, it was stabilized in a transition orbit between the main asteroid belt and the Earth. And then through a further, probably gravitational encounter with the Earth, that orbit was circularized so that it became a near-Earth asteroid. Now that's complicated, but we believe that's what happened, and people have spent a lot of time modeling this on computers and making sure they can compare Bennu with spectroscopically with other asteroids in this family to convince themselves that this is what happened. Okay, now this is the part of the talk where I ask you to pull out your anaglyph glasses. Now it's okay if you haven't gotten them, but if you do have them, put them on now and you'll see 3D rotation of the asteroid after we approached it in fall of 2018. Now, just gonna pause here while people can get it. And I'm gonna get out of share mode so you can see me with my anaglyph glasses on. So these are red-blue glasses. Let's see, which one is which? Oh yeah, blue on the right, red on the left. And I've shown in the anaglyph 2 different versions of the same image, one red and one blue. So the right eye sees one image, the left eye sees another image. It looks like the eyes are seeing parallax, so you see 3D. I hope that's clear, but we're going to be talking about it a lot more. It's cool. Right now, I'm looking at my screen, and I can see three 3D versions of Bennu coming out at me from the screen. Okay, I'm going to do a little quick check here. How many people are actually got anaglyph glasses here?
I'm not hearing much. I know I don't have a pair, so I'll have to watch it on YouTube again, I guess.
All right, fair enough. I'll keep going, and I've got stuff that's not going to require anaglyph. So let's see, I don't want the screen. I want this one. Yeah. Okay, so I'm back in presentation mode now. Okay, so on the left was a movie made up from time lapse from a period of 2 to 3 months as we approached the asteroid. We started seeing it finally in August of 2018 as a point source, and then by December we were there as we approached pretty slowly for a spacecraft mission. Usually when you're on a spacecraft or investigating and exploring the solar system, you are moving at kilometers per second at the minimum. But for us, we're going to a zero gravity object. We don't want to use a ton of fuel. We don't have as much of a time constraint because there aren't any scary encounters that require us to be pinpoint accurate to a tenth of a second or anything. So we approached in a leisurely and safe fashion. The anaglyph on the right, by the way, was constructed because we took a series of 36, or was it for this one, 24 images? I think this was 24 because the 3D is pretty extreme in the right, and it's kind of, you don't get a choice as to the amount of 3D that you have to put in the anaglyph. But basically, you take successive images adjacent to each other, and you show one only to the left eye and one only to the right eye, and 3D results. Okay, so I'm going to show this one. Now, this on the left here is another form of this 3D stereo, and I wanted to show it here just because some people might be able to see it. The trick is let the right eye look only at the right image of the asteroid rotating. That's on the leftmost frame, and let the left eye look only at the left image. Now, it's a little bit hard to do. You have to parallelize your eyes, and that is the opposite of doing cross eyes. So instead of doing cross eyes, you're going the other direction. And when you do that, you see a third image or a fourth image even, and you basically try to take the two middle images and bring them together. And one thing you can do to help this process is to take your hand and stick it, and I'm going to go out of share again and go into, so you can see me. So you take your hand and you do this. So it blocks your right eye from being able to see the left side of the image, the left image, and it blocks your left eye from being able to see the right image, and they each are confined to their own little corridors. So I'm going to put it back now. Hopefully I won't cause everything to crash in a whole from all this shenanigans. Okay, here we go. So the free view stereo is back on the left. On the right, of course, is the anaglyph. So if you have anaglyph glasses, you're able to see that, no problem. But on the left, you'll try to do your eyes parallel, and then in the middle, you should see 3D pop up. So I'm just going to pause for 10 seconds and let people try to do that. I tried to make the sizes and the presentation appropriate for people sitting at home, watching their computer screen, and being able to do this free view stereo. If you can't do it yet, don't worry about it. There'll be other stuff. All right. This is just a regular flat rotation movie. It was taken the day after the other two movies I just showed. And basically, it was around December 3rd, I believe. We had just gotten to the asteroid. You can see the phase angle is already higher than the phase angle in the previous images. We're not looking at a full illuminated disk. We're looking at a mostly illuminated disk here. And you can see shadows cast by a lot of the features. And the first thing you see is that Bennu is a very, very rocky place. Now, this caused some heartburn when we first saw this, because the first thing we thought of was, where are we going to get a sample from? You know, we need to be able to have a relatively smooth area with a regolith and not any scary boulders nearby so that nothing bad happens to our spacecraft or our TAGSAM arm. So at this point, we started thinking about a more accurate targeting. Rather than an error of 25, or 50 meters, we were thinking about errors closer to 2 to 5 meters, and we changed our technique. So we got there at the end of 2018. Just as the new year was starting, we entered orbit around Bennu, which was set a record for the smallest body ever orbited by a spacecraft. And almost immediately we discovered particles being ejected from the surface of Bennu, which caused a lot of consternation. So we tracked these particles, and I'm going to show you in a second what they look like tracked. But you can see the particles here. This is actually a composite frame. If you want to see the particles, you are way overexposed on the body of the asteroid. If you want to see the body of the asteroid well exposed, you cannot see the particles. So those are two different exposure times. So this is a composite form from those two different kinds of images. These on the right is a day of year through most of 2019, and we can see events marked here of when we observe particles being ejected. So they're not this is not happening all the time. It's happening aperiodically. And once you try to track the particles, you find they have really nice, weird, stable, unstable orbits. Sometimes they can stay for a long period of time. And just see that event. A bunch of particles were ejected all at once there, and some of them enter orbit, some of them fall back, a lot of them fall back. Some of them are ejected out of the Bennu system. There was a working group formed to study these objects. This was a completely unexpected phenomena. It had been speculated about, and we had searched for it, but we realistically did not expect to find it because no hint of it had ever been observed from the ground for this particular object. But there they are. So we started cataloging them and modeling these events throughout the rest of the time. And you remember yesterday I was saying, you got to try to make lemonade out of lemons. Well, yes, we had these scary particles being ejected through the regions of space that we hope to fly the spacecraft. But one of the cool things about modeling these events is that you can get a much better idea of the internal gravity of this object than you would have gotten just from studying with radio. So now we had a way of confirming the gravitational term determination that we were going to make through observations of Bennu's shape and assumptions about its interior density. We were going to be able to confirm them by studying these objects. So that was a really cool thing. And the flight dynamics team at JPL, who is headed by basically Steve Chesley's group, had a fun time trying to model these things. Okay, here's another anaglyph stereo movie on the right there. Most of the time that we were at Bennu, we were in a stable terminator orbit. Now, what is that? Well, it's an orbit that follows the line of light and dark on Bennu. So Bennu, always, like all objects in the solar system, has one face that's facing the sun. It has a face that's dark. It rotates, so the surface itself is moving in and out of the bright area. But if you're a spacecraft around a very small object and you want your orbit to be stable, and if you while I'm talking, you guys should have your anaglyph glasses on, those of you who do, and you can see a lot of the images that we took from this safe orbit. The sun will be shining on you from the left. Gravity from the asteroid will be pulling you down from the right, basically pulling you in. So the two work to create a kind of dynamic equilibrium, so you're in a relatively stable situation. Any other orbit that you take around this thing will ultimately be unstable. Even this orbit is ultimately unstable, but it has a much longer lifetime than any of these other objects. And NASA's not interested in perfections per se, it just wants good enough. And good enough here is if you can guarantee several weeks of stability to your spacecraft, then it's allowed to go into safe mode, and you're allowed to recover from safe mode, which happens to these really complicated instrumentations. you can recover from it and still not threaten the mission. And that was kind of the criteria that got these orbits selected. You can see that we predominantly spent time in two different orbits. They're indicated here. The outer orbit was the one we first got into, and that's actually the harder orbit to take in orbit because gravitation is less than. When you go closer into the asteroid, and this is the orbit we spend the most time in, you actually have a more stable situation. The problem with that is that you can't take decent pictures. The pictures are going to have a ton of shadow in them because you're taking them at 90-degree phase angle, or phase angles even higher. And they look like what's on the right, which is very interesting. And you're able to see a lot of detail, especially with the polycam, because it's only 680 meters away from the surface of the asteroid. And so you're seeing stuff with, centimeters of resolution, which is really quite good for a planetary mission, especially on a routine basis. And you're able to take enough images, you can make 3D stereo anaglyphs out of them, like I'm showing this movie for. But the darkness of a lot of the shadowed regions prevents these from being perfect images that you can, more importantly, manipulate to make mosaics and stuff. So you have to leave this orbit to take decent imaging. And that's what we ended up doing. Now, this one, I'm showing another view. This doesn't have the anaglyph stereo on the left. So you can just see the dark. This is the famous kind of, or iconic kind of boulder that we saw on Bennu predominantly. And I show them in 8 different stages from least weathered to more weathered. So boulders on Bennu show a ton of degradation, and there's some of them show a real extreme amount of degradation. So I show that in the GIF on the left there, and it's not in anaglyph stereo, so you're able to see it pretty well. And I'm just going to let you take that in. These are all images that were taken from the relatively stable, safe orbit, by the way. So you can see there's a ton of stuff you can see. It's just that you can't map and you can't survey very well. So we're going to fix that by leaving orbit. Now, yesterday I said that individuals among us will make mistakes. We're all going to make mistakes, but together we hope to be perfect. And this is a bunch of words on a slide that basically spell out in detail how we were going to accomplish that. And this is actually how we conducted this mission, at least most of it, and how we planned all of our campaigns. They were planned within a rolling 8-week window. So we were always planning one of 8 different campaigns. So week after week after week, stuff would happen. And this is during the most intense 2-year period when we were conducting proximity operations around this asteroid. We would start the planning week 1. The planning would get more sophisticated in week 2. And then we would start the planning for another week in week 1, all happening week after week after week. And so there are tons of meetings, tons of various stages in the planning process. And at each stage, you're getting checked in a very systematic and thorough and formalized way. We're all checking each other. So I wrote the words to describe this process on the slide. I don't expect you to read it, of course, but I just wanted you to see what this reach for perfection looks like in real life. Okay, so I said we have to leave stable orbit, and let me do a time check here. So I'm at 40 minutes, which is not bad, but I'm a little behind. Let's have any questions. Any questions at this point, Kenny? Hearing none, I'm going to go. Can you guys, am I still going? Can you guys still hear me?
Yep, you're all good. Sorry, I hit the wrong
good.
button, but no questions. There is a couple teams with the glasses and they are working, so.
Oh, perfect. All right, great. That's good to hear. Sorry, I'm so stubborn. I have to include these anaglyph images just because it's cool. All right, so we leave stable orbit, which is shown in red here, and we travel out using not very much delta V at all. You can see the spacecraft there. It's a little bit big compared to the body of the asteroid, but it's big enough to see, which is why it's that big. We're talking about 10 centimeters a second, 20 centimeters a second of delta V. Those are micropulses for all intents and purposes. And we can get down to a few millimeters per second delta V with our really tiny thrusters. That's all you need to do to navigate around this asteroid and station keep. So that's what we were doing. We'd move around to the front of the asteroid, Now, it's weird, but the front of the asteroid is actually a dangerous place because the sun's shining from that direction, and the sun's radiation has solar radiation pressure, and it can push you into the asteroid, change your orbit so that it becomes more unstable. So you're only really doing this for a few hours at a time, and then you go right back into the safe orbit and catch your breath. This is, and I don't expect you to read this again, but these are our campaigns that happened between late 2018 and late 2019. So this is all the stuff that we did, and probably just an abbreviated version of it. But these are all the campaigns that gave us our imaging. And through the course of the mission, we've taken something like 63,000 images, at least with my cameras. And then with the OpNavs, probably tens of thousands of more images. I wanted to show you some few images from this imaging campaign. You can see the illumination geometry in this image is a lot more favorable than the images taken from stable orbit. And it shows this beautiful boulder here, which has always intrigued me because it looks a lot like marble and is very unlike the most of the boulders that are on Bennu, which are these dark, hummocky, degraded things that they look like they're about to fall apart. So I made an anaglyph stereo of it. And the pair that you just saw, and you should, if you put on your glasses, you can see that thing coming out at you, 3D coming at you. So I'll just pause here for a few seconds. So that was one cool image. And mostly what we wanted was to make a huge global mosaic of the surface of Bennu, which we've done here, I'm showing here. And based on this mosaic, identify primary and backup sample sites, which we did. So we code-named these sample sites. There were 4 originally. We named them after birds because the theme for Bennu was mythological birds. For the primary site, which we called the Nightingale site, and the backup site, which we called the Osprey site. And you notice Nightingale's up at higher latitudes, almost 60 degrees. The backup site was nearer the equator. So this actually is a little bit easier to get to because one of the requirements was that we were in constant communication capability with the Earth, and that was easier to do at these higher latitude sites and not be as intensely hot as you are on the equator. So we didn't want to bake our sample that we would get. So the primary site ended up being the one that we went to. These are close-ups of the sites. You can see they're fairly boring, safe, and as the most hazard-free we could find on Bennu. I've indicated the dimensions of these sites here. You notice that, and let me try to move this here so you can see there's no good position. It's unencumbered. You can see 24 meters. The primary site is right here and it's pretty big. There's a lot of space that you could imagine sampling without getting too close to these boulders. And that's kind of what you wanted. This site is a little bit worse, but also pretty good. So let's get back on. So having identified these sites, we had to validate them. In other words, we had to guarantee that there was material at these sites that we could ingest with our sample head. And our sample head, the mylar flap opens to about 2 centimeters. So anything bigger than 2 centimeters was going to jam into the mylar flap between the flap and the interior of the sample head, and the thing would be stuck. Now, as it happens, that happened anyway, but we're not supposed to know that at this stage. So what we were trying to do was guarantee that there were pebbles on the surface, grains that were less than 2 centimeters in diameter. And we did this by getting real close to the surface of the asteroid and imaging with our highest resolution camera possible. So I'm going to show you a succession of 4 or 5 images where we get closer and closer from different campaigns. So we identified a flat area, a flat bouldery area, and you can see this flat area here. This thing has absolutely, it looks very featureless. So I considered it like a witness plate. So I was going to look for stuff on that face, and you can see it here at higher resolution. You can see this is the area I'm interested in. This is from a safe orbit, so you can see it's very shadowed because we know stuff from safe orbit has got a very high phase angle. And then this is during low recon, and we're imaging that same block and looking at it really closely. And when you do, you see stuff that's smaller than 2 centimeters. So we established or validated our sample site here in this series of observations, which actually was a very important thing to do. Remember, I'm telling you about the difference between engineering and science. This was an engineering thing that had to be done before we were able to move forward with the sampling. So having done that, we moved forward with the sampling, and I'm showing you this same GIF that I showed yesterday, which is this really violent, really quick. You know, I'm sorry, I grew up in the punk era, so I'm my sensibilities, while nerdish, are not completely so. But I'm going to show you a much more tame version of this, which is much more informative. This was done by a friend of mine, and he, at the same time as we displayed the SAMCAM image sequence on the left, he displayed the navigation camera image sequence on the right. This is the actual camera that was doing feature tracking, so taking images and comparing them to a database to figure out where we were relative to the sample site. This was the succession of images that it was taking to accomplish this. You can see we're getting close to the sample. You can see the sample arm shadow moving across the frame on the right, and then on the left, and bam, all heck breaks loose. And then we start pulling away. You can see the boxes getting bigger in the center. Those are overlays on Bennu's actual, you know, north latitude is up, east latitude is to the right, kind of mosaic map. And then we pull away, and then the thrusters fire, and we're out of there. And at the time, thinking we would never return, but NASA really wanted to farewell tour images, and I'll talk about that in a second. So those are the, of course, being me, you guys know me by now, I couldn't leave that alone. I had to show just the explosion. So this is all the exciting stuff happened into just a 3-second GIF. You can see us going back and forth to the sample site. So we disturb the thing like crazy and just send out a spew of rocks and dust. And it's interesting, but if you, okay, I was gonna show, I'll come back to that one. This is a GIF for the closest images we have to the tag bottle gas release. And these are nav cams, by the way, not SAM cams. And the first one is just before the tag bottle release, and the second one is just after. And you can see a pile of dust there, but not a lot of rocks. So this is too soon for the rocks. They're more massive, so they have greater inertia, and they're harder to speed up than the dust, which just takes a squirt of gas. And you can see it darken the frame, and you're able to measure the optical depth. And in fact, I've outlined several rectangles, these little tiny white rectangles, where you can measure the optical depth and deduce how much mass we kicked up, and hopefully the initial layer thickness of a lot of this dust. Okay, now back to this. This is another anaglyph on the right. It's a anaglyph stereo image on the right, and on the left, a free view stereo. And this is just before we hit the surface of Bennu. So you're able to see the surface in 3D. And I didn't do this, by the way. I created the anaglyph, but on the left, the free view was created by Brian May, who is, in fact, the lead guitarist for the group Queen back in the 80s. And it's appropriate for my sensibilities. And he started out as an astrophysicist and got involved in the mission, and really loves this sort of free view stereo, which I do too as well. So I'm not the only one. So you can see it if you put on your glasses or do free view stereo on the left. You can see the sample site before we disturbed it in 3D, which is kind of cool. All right. So having tagged and created a sample. So I've got 10 minutes, so good time to take questions. Any questions so far?
No, we're good. The only one question that I would see is, how long does it take to retrieve the data from the probe as you're doing this?
About a day to 5 days, depending on how much data you have. So we have a fairly generous downlink rate, considering that we're a circum-Earth object or near-Earth object. So we only have like a 15-minute light travel time. And so that gives us we're about 1 AU or 2 AU away at the worst from the Earth. So we're talking about 600 kilobits per second to 1.3 megabits per second, something on that order, 900 kilobits per second for a lot of that time if the deep space network is being generous. So we can download, I don't know, 1,000 images in a few days, something like that. So there's a lot of stuff happening with the deep space network because they've got to service a lot of spacecraft missions that are out there. So we have to reserve the time, and the time window has got to be sufficient to download the data and yet not have anything untoward like the system going down in the meantime. So every now and then the system goes down. You'll have data dropouts and you got to fill them in later. Okay, so having tagged, we looked at what we got, and I showed you this yesterday, but I didn't show it to you as quite this fashion. This is another friend of mine, Christian Dobany, who processed these images so that you can actually see the locations and sizes of the objects that were being released from tag. So it's kind of cool. Okay, here's another anaglyph stereo. This is before and after what we did to the sample site in 3D. And if you look at this, you notice that on the right, it's way darker. And that's not an artifact of the stretch, that's actually real. We blew off a lot of stuff, and the surface stuff apparently is brighter than the interior stuff. So radiation damage and exposure to high energy particles from the sun and from galactic cosmic rays apparently brighten stuff and make stuff bluer than the stuff that's in the bulk being hidden from all that cosmic radiation damage. So that's an interesting thing to figure out and to know. This is a GIF with no anaglyph glasses needed. It basically shows the before and the after, and you can see that there was one boulder there that we kicked up. It's the one that's circled in the red here. We kicked up and mobilized to go, about 10 meters, which is quite astonishing. The mass of that boulder is probably on the order of 1,000 kilograms or a ton. So that's remember, this is 0G. So all that matters is the amount of energy and momentum that you inject. You're not going to have any friction per se from an atmosphere. So you could launch stuff a long way, apparently. You could see that we disrupted the tag site. In general, the GIF here doesn't have a very revealing stretch, so it's just sort of bland. It's hard to know sometimes how to stretch these images, whether you want to preserve the reflectance on some kind of linear scale, or you want to reveal more detail. And then this is the last look that we had at Bennu. This was taken about a month ago, April 9th or so. And this is what a mosaic of a bunch of images, a couple thousand, I think. And we are basically our last look at Bennu. The tag site is up in this area. This is Boulder Town. This is the big rock, they called it. And it's our last look at Bennu. And this is our last look at the sample head before we stowed it in. You can see a lot of particles clinging to the interior of it. There's particles clinging to these contact pads. You can see one poking out there, another one poking there, another one there. That they were designed to collect surface particles so that we could study them separately from stuff that was in the bulk or beneath the surface that would all be mixed together in the sample head. And that is it. I will take questions now.
All right. The other question I've gotten here is, do you think Earth was seeded from the asteroids and comets?
Well, the water on the Earth, most people believe the water on the Earth came from asteroids and comets. I mean, you saw those videos here. Here, let me see if I can put it up again. Those videos of the early solar system show that a lot of stuff got kicked out. So most of the stuff that we see today, and let me go back. Close your eyes, you guys. I'm going to go really fast. There we go. Most of the stuff that we see today moving around. So look at this first. This is solar system origins. All that green stuff, that was the original complement of asteroids and comets that the Earth had, minor bodies that the solar system had. Most of those were kicked out or kicked into the sun. And the remnants are what's on the lower left. right? I mean, as many as those are, more than 1 million by latest count, they're still nowhere near the amount that we had at the beginning of the solar system. So if something is in an orbit and it's a minor body, even if it looks like a mess, a hot mess here, it's like a part of a precisely synchronized and timed Swiss watch almost. I mean, everything that's in these orbits here is there because it has managed to mediate between the forces of all the larger bodies around it and make them happy so that they don't kick it out of its orbit into something unstable. That's the solar system that we are left with today. So all of these bodies that were kicked out, a lot of them were kicked into making the Earth, making Venus, making Mars, the bodies closest to us in the solar system. In other words, the large bodies. They have water because of these bodies. The water that we think formed in the outer solar system. You see where all the green is here. That's where we think the water formed because that's where it was cold, and that's where the water and especially the hydrogen could be retained. So it was delivered to us by gravitation and by this process of solar system formation, and not just the water, but potentially the materials for life, all the carbonaceous materials.
Very good. That was our last question, actually. I think everyone's just sitting in awe looking at the 3D images and not typing. So I think that's absolutely great. But from the Rockets for Schools Committee and from all the participants we have this year, I appreciate your time last night and today, sharing your wealth and your excitedness over science and space and the planets. And we look forward to hopefully talking to you in person maybe someday too, or again next year, maybe with a further update on the whole system.
Thank you, guys. Thanks.
Sounds good. Well, pleasure meeting you, sir, and I will let you go. And again, thank you for your time.